Good morning, good afternoon from the International Society in Quantization, Geometry and Dynamics, ISQGD. ISQGD is a non-profit, community-driven global society dedicated to serving the worldwide mathematical community and advancing mathematics from K-12 education to frontier research. Today, it is my great pleasure to introduce ISQ distinguished speaker, Professor Sascha Troscheit, a leading researcher in modern analysis and geometry, whose work has significantly advanced our understanding of fractal structure, dimension theory, and random geometric phenomena. He is currently an associate professor of mathematics at Uppsala University, Sweden, where he is actively engaged in cutting-edge research at the interface of probability, geometry, and dynamical systems. Professor Troscheit is internationally recognized for his contributions to fractal geometry, geometric measure theory, and random dynamical systems. His research focuses on the fine-scale structure of sets and measures, particularly in random and self-affine settings, and on the behavior of various notions of dimension, including Hausdorff and Assault dimensions. His work has deep connections with probabilistic methods and has contributed to the understanding of scaling laws and geometric properties in random environments. He obtained his PhD from the University of St. Andrews, where he developed foundational results in dimension theory of random self-similar and self-affine sets. Since then, he has held several prestigious academic positions and has collaborated widely across the international mathematical community. His research continues to influence contemporary developments in fractal analysis, embedding theory, and metric geometry. Through his insightful and rigorous contributions, Professor Troscheit has helped shape modern perspective on randomness in geometry and its interaction with dynamical systems and analysis. We are truly honored to have him as a speaker in the ISQGD Distinguished Lecture Series. Please join us in warmly welcoming Professor Sascha Troscheit to the ISQ Distinguished Lecture Series. Professor Troscheit, the floor is now over to you.
Great, thank you very much. Let me just share my screen first. Let's see. Hopefully this is now visible. And forward, back. Okay, great. Yeah, thank you very much for the introduction and for the invitation to speak. So my talk is going to be about some work I did a couple of years ago with Kenneth Falconer on sets in random geometry, whatever that means. So let me just kind of set the scene. I'm not really assuming much background in fractal geometry, though I suppose many of you have some knowledge there. So let me maybe just give a kind of a dimension theory primer. So what's the basic thing that we're interested in is well, a dimension. What is it? Well, it's a number. And what does it represent? Well, if you want to interpret it rather broadly, it is some sort of number that represents some growth of complexity with scale. It's intentionally vaguely described because it can mean many, many different things depending on what properties you're interested in, how you want to measure complexity, how you want to measure scale. So maybe in metric geometry, a few of the important ones are the Hausdorff dimension, which, well, there's a definition here. You can ignore it if you want it. What does it do? Well, it measures how easily a set is coverable with covers of arbitrary sizes. So you have some set here for illustration purposes. I have the set 1 over n, discrete set, and we're trying to cover it in a very efficient way. So it's the least exponent such that we can cover it with some set ui. So here these are these balls. We are taking a look at the radius or diameter, raising it to some exponent. We're trying to have this summable. And we're trying to do this in FEMOM over all possible covers that exist. And the Hausdorff dimension is the least exponent you can get away with some cover. And if you have something discrete, well, if something's discrete, you can cover it incredibly well using balls that shrink exponentially or even super exponentially. And you can start off with any possible size. So for any exponent, this is as small as you would like it to be, positive, but as small as you want. In fact, this means that the Hausdorff dimension is 0. And this is true for any countable set. There are other dimensions. So here we have all possible covers of all possible sizes. And we're taking the best, the optimal cover for this. But we could have also taken covers of the same size. That's the box counting dimension. What I'm defining here is really the upper box counting dimension. Let's not split hairs. So it really is just saying, okay, we're looking now at covers of balls of the same size R, and we're trying to bound the number of balls that we need. So in a similar way to what we had before, the sum, we now are just counting all of them. And we're again looking for the least exponent we can get away with, such that the number of balls that we need of size R shrinks at this right exponential rate. Now, there's already a little bit of a difference between the Hausdorff and box dimension for this set. The box dimension is going to be a half. And this comes about because we have restricted the size of the sets. So in fact, on this left tail here, we need quite a lot of covers at every scale to cover it. And if you think about the definition, I haven't seen this before, might be a nice exercise to see, well, the box dimension is always going to be an upper bound to the Hausdorff dimension, mostly because this is any possible cover, including same-sized covers, and this one is a specific type of cover. All right, so we have 2 dimensions already. The third one that is of interest, at least to metric geometers, is the Aswad dimension, which tries to do the same sort of thing as the box counting dimension, but it tries to do so locally. So it tries locally within a ball. We're trying to cover it within that ball and rescale it appropriately. Don't worry too much about the definition. Essentially, it's kind of a local version of the box counting dimension. Because it's a local version, the dimension can increase even more. And in this case, the dimension is 1, so even larger than the box counting dimension. That basically arises from things just bunching up here to the left. And if you zoom in closer and closer around the point 0, what you'll find is that these points get closer and closer together. So it, in the limit, whatever that means, it looks a little bit like a line. It's still discrete, but from a covering perspective, it looks like it's the entire space, like an interval locally. All right, so you have these 3 dimensions. Keep them in mind. So Hausdorff, efficient covers, box counting, same size covers, Aswad, worst possible covering, or the thickest part of the set. All right, and yeah, you have the relation. The first one I already mentioned. The second one also holds because, well, if we are looking at the worst possible local cover, we can just take the global cover, and we still need to cover that as well to have any local covers. So it's also an upper bound, at least for bounded sets, for the box counting dimension. Okay. Well, what's the dimension? Well, it has some nice properties. So if your set is regular enough, then all of these things agree. So if you have some finitely many points, it's 0. If it's a smooth curve, it's going to be 1. Dimension is 1. Smooth surface 2, etc. In fact, if you have a space which is regular enough, so something which is alphos regular, alphos David regular, if this is alphos regular for exponent s, then all of these dimensions coincide. Alphos regularity means that really locally these covers scale at exactly the right rate. And it has as a consequence that all of these dimensions are the same. So many people are interested in these smooth settings or these homogeneous settings. I'm more interested in when these things break down and you have a bit more local variability. And what I want to try and do is learn more about geometric objects, about these dimensions, and take these dimensions as kind of data points of how coverings locally change and what one can say about the object with these. All right, so let's take these kind of notions and throw them at something. As mentioned in the introduction, I'm very interested in random sets. I'm not really a random geometer in the geometry sense. I'm more of a fractal geometer, if you want. But random geometry is a big subfield of probability which tries to study canonical examples of random metric spaces. So you have a metric space, and it arises from some stochastic process. Somehow it's a randomly given metric space, and we want to study their properties. I'm a dimension theorist, so I'm going to throw dimension theories at them, but there are many other things you could do with these. In fact, one of the kind of popular ways of creating these random metric spaces is to take some classical space, RD, unit cube, sphere, whatever it might be, and create a canonical random metric on it. One example is the Brownian map, which also arises as a scaling limit of planar maps on the sphere. So there are many, many connections with other things. So in this case, with random graphs and taking limits there. There's also Liouville quantum gravity. It arises in conformal field theory. I don't know anything about it, so don't ask me questions about it, but it arises as a natural object there as well. And in fact, for some specific values in this parameter with which you create Liouville quantum gravity, these two things actually happen to be the same model. And then lastly, what I'm going to talk about today are multiplicative cascades. I'm going to talk about them in R. I think they look a little bit prettier in R2. And this is an idea of what this should look like. It's an idea of what a measure in 2 dimensions would look like, this multiplicative cascade measure. Maybe let me just say some words about these spaces, just to have some idea of what these are. So this Brownian map arises as a limit of large random maps. So you take a quadrangulation that's on the sphere. Okay, I've embedded this planarly, so this is not really an embedding in the sphere, but let's ignore that. We just try to triangulate the space randomly and see what happens with the graph that we get from it under the graph metric suitably rescaled. And taking a limit, believe me that you can take a limit in some sense, gives you a random object. This random object happens to be the Brownian map. This Brownian map is a rather interesting space. It's still a sphere, at least from a topologist's perspective. It's homeomorphic to S2. But its dimension theory has changed. The random metric causes the dimensions to change. In fact, it jumps up to dimension 4 for both the Hausdorff and the box counting, but its Assoit dimension is actually infinite. So locally speaking, it can be quite wild as a metric space, but globally, if you try to cover it either with covers of the same size or even with efficient covers, it still looks 4-dimensional instead. Liouville quantum gravity, I'm not really going to say much about just how it's defined. It's if you want to think about, once we've done multiplicative cascades, it's kind of a more advanced version of these. It tries to have some distribution that's conformally invariant, which is what people care about in geometry, and builds a random metric space that has some nice geometric properties. But for the specific value that appears in there, think of it maybe as heat or some local properties, this happens to be the same as this, as the Brownian map itself. All right, but let's just keep the name in mind. Liouville quantum gravity is essentially also a random sphere or a random surface. All right, and now to the star of the show, which is this multiplicative cascade. The multiplicative cascade arises from taking a random variable. So it's kind of nice construction. You just take one specific random variable, infinitely many copies of them, and you're dividing the space into cubes, subcubes, and divide those subcubes into subcubes, and change the density there with this random variable. We maybe be a little bit more formal. You have this random variable, W, positive, almost surely non-constant. We want something trivial, and we want its expectation to be 1. So if you sample this often enough, on average, the weight of these should be 1. There's some technical condition that we need, so which is this condition here. Ignore it. This just makes sure that things later on converge. And then what do? Well, we look at all the dyadic intervals, and we take our original interval, let's say the unit interval 0, 1. We divide it into 2 parts, the left half, the right half, And for each of these two intervals, we associate one random independent copy of W with it and weight the density by this W. In fact, going through all of these dyadic intervals, we label them in the usual way with some zeros and ones. And what we then do is we associate to every one of these dyadic intervals that's indexed by the sequence of zeros and ones with this multiplication of these copies, so that we have our original interval, then we've taken the first sub-interval dyadic, we get a weight of this, which is Wi1. We then subdivide it again, and then the next one is the weight that we're giving is this here, and then so forth and so forth. We associate weights for every one of these dyadic intervals. And we don't stop there. Well, once we have this dyadic interval, we have to continue ad infinitum. And in, well, the easiest way to write this down or to define a measure there is to say, well, okay, we define this M approximation measure of an interval to just be this product that we have. So it's a density, so we have to multiply it by the actual length of that dyadic interval of length k. But it also gets multiplied with this tail. And this tail is really just, you do this at infinitum and you sum up everything below it. This thing is a really nicely behaved random variable, so really you can just ignore this for now. For instructive purposes, you just take your dyadics and you associate a weight with them. Because this is so central, I'm going to give you a couple more ways of defining this. So let's look at the densities. So on the left, we've just started. We have the unit interval, density 1. Great, this is the cumulative distribution function. And we divide it into halves. We now give them a randomly chosen weight. In my example, I'm choosing a weight a half or 3 halves independently with probability a half. So expectation would be 1. So here, the next one, well, we happen to choose for both of them a half, which means that the density drops down to a half. Notice it's a log scale. Just because we're multiplying things, this will be a little bit more instructive. But now the density is everywhere, it's a half. So the cumulative distribution function also just goes up to a half. Now we divide all of these two halves into subsequent halves, multiply them with independent copies again, and now we happen to have this distribution. And we keep on dividing and multiplying and keep on dividing. And what we end up with getting is well, a random density. The density doesn't really make sense. This thing doesn't converge, but what does converge is the cumulative distribution function. That actually converges to something reasonable. And this cumulative distribution function uniquely defines the measure. So actually the measure is nicely well defined. This density only works as finite approximations. But kind of from an intuitive point of view, this is maybe reasonable. All right, so we now have this random measure, and using standard martingale techniques, you can show that this actually converges to something. There actually exists this limiting measure. And with these conditions that we had in the beginning, we are also can say that the measure is finite and non-zero almost surely. I'll repeat that in a second. But maybe let me do one more thing of how do we actually get random geometry out of this? So we have a measure, but how do we do random geometry? Now there are two ways of thinking about this. One is that we look at sets and as a subset of the unit interval, and then just map this under the cumulative distribution function to another set. This now gives you a random set. The other way of thinking about, kind of equivalently, is that we had our unit interval from 0 to 1. And what did we do? Well, we split it into halves. Then for each on the left and the right, we associate a new copy of this W. So the left-hand side may have gotten just weight a half, the right one 3 halves. So, okay, both of them together, we still have an interval of length 1. But then we divide these into halves and now weight them again. So now the next random draw of our W's gave us a half, 3 halves and a half. So if we now skew all of these lengths by exactly that factor, what we get is something that changes the local properties a little bit. And what I'm claiming is that you can do this ad infinitum, and you look at the cumulative distribution function, and this tells you some random geometry of the space. All right, so we had this condition. This condition is nice. It essentially just tells us that this measure, the measure of the unit interval, is well defined. It's not trivial. It's going to be a positive finite number almost surely. It also has no atoms. Every interval has positive measure. It's kind of as nice as you could want kind of fractally measure to be. And from all of this, we of course then also get that the distribution is some strictly increasing continuous function, almost surely. I might forget saying almost surely in the future. Essentially, everything I'm going to talk about from now on is an almost sure result. Okay, so we have this measure now. And what we're interested in is studying objects with this, with random metric induced by this measure, which is this one here. So the measure between the distance between 2 points is just the measure between these 2 points, the interval between them. Or if we're interested in properties from a dimension perspective, we can equivalently analyze just the kind of the push forward, the image under the CDF of that set instead, but keep the same Euclidean metric, which is also what I'm gonna, as an interpretation from now on, go on. But all these results, I mean, this is just equivalent settings, these two metric spaces. Okay. All right, so that's the random cascade. So let's move over to a little bit of physics, mathematical physics. The KPZ equation arose in the 80s as an interpretation of, well, if we have a random geometry, whatever this might be, some nice conformally invariant random geometry, going through this computation, what you would expect to happen to things that are in Euclidean geometry, have some dimensions, some scaling properties, you now put them into random geometry. These scaling properties should change depending on this random geometry. And well, the KPZ equation relates these two scaling properties, and it predicts from a more physics, let's say more heuristic perspective, that the dimensions are related essentially as a polynomial of degree 2 in this form that you have the original scaling rate times 1 minus that rate. Ignore this is just a constant. Tells you something about the difference between these two dimensions, these two scaling properties. This thing down here, this k+2, really is something more related to the actual model, so some sort of temperature or some sort of local property that you have, which just scales it by, well, a scalar. But the important thing to remember is difference is related to the original as this dimension 1 minus dimension relation. Okay, so one of the first few things where this was proven to kind of hold was in this setting of these random cascades. So Benjamini and Schramm in 2009 proved the following. So under some technical conditions on this random variable W, if you now have a set which is a subset of the unit line and you know its dimension D, what you're interested in is what's the dimension of this set E under this random metric. And they prove that the Hausdorff dimension is exactly this value S that satisfies this equality here. So it is 2 to the dimension, the original set dimension, and then it's 2 to the S, and you normalize this by this kind of this S moment expectation. There's a unique S that solves this, and that is the dimension of this set under random geometry. In fact, if you want to go for an example, well, what's a nice W, nice random variable? Well, normal distributions are the right things to look at in probability quite often. And because it's multiplicative, okay, we have to take the log normal distribution, or the logarithm of W having normal distribution. But if we assume that, then this dimension prediction here becomes the following, that the difference between D and S is some constant times S1 minus S. But this is exactly the KPZ equation. So if you have random cascades for nicely behaved random variables, and you nice relationship, this quite simple relationship between the dimension, but if it's a log normal, you do end up getting this KPZ equation. All right, so that was maybe the first to formally prove this sort of relation in some sort of in some well-defined random geometry. A little bit later, maybe I should say this. This condition that I keep on using, this expectation of W log, maybe let me go back. Where is it? This condition here, being less than 1 is usually assumed. This is subcritical. You can take it to be equal to 1 if you mess around with the measure a little bit. That's called the critical case. So this work here also holds in the critical case if you change it appropriately. That was done by Barak-Kupiainen, Saxman, and Webb. I think it was 2012, thereabouts. Okay, but so this is random cascades. If we go back to Liouville quantum gravity, this inspired work by Duplantier and Sheffield, who also proved that this KPZ holds there. So it is this value here. Okay, there is some exponent here, something that depends on the exact distribution, but you get this KPZ relation again. I have to maybe say here that the dimension that they use is not the Hausdorff dimension. As far as I know, this might... Oh, no, this is no longer open, but this was open for quite a while, still longer. But what they used was an expectation of box dimension, but not really the box dimension, but rather evaluating the box dimension in expectation, which may not be the same as the almost sure box dimension. And this difference is actually quite important because this average of box counting, the box counting dimension does not necessarily behave very well under projections, but also under this change of random metric. And that's kind of maybe the highlight of what I want to present today, is what happens in the setting of the multiplicative cascade with the box counting dimension instead. So this is my main question for today. So what can you say about the upper and lower box counting dimension in the cascade setting, the actual upper and lower box counting dimension, not an average version, and perhaps the packing dimension? Yeah, so the box dimension doesn't play nice with projections. It's been a kind of long-running theme that one needs to use some different machinery because you're looking at coverings of the exact same size. Once you change their sizes, where you're taking the same size cover in this image becomes much more difficult to handle. So what did we do? Well, Kenneth, Falconer, and I, we looked at what happens with the box counting dimension, and very early on, and this is a fairly short proof, you can show that this value that is predicted by the Benjamini and Schramm result always gives you an upper bound. So if we have some subset, we know its dimension to be some value d, almost surely the box dimension of this randomly transformed set is bounded above by this S, which solves this Benjamini and Schramm equation. So in particular, what this means is that if you have a set which has Hausdorff and box counting dimension the same, well, if the Hausdorff and box counting dimension are the same, the lower bound will be given by the Benjamini Schramm result. And now, if you take the box counting dimension result from us, that as an immediate corollary has that the box counting dimension is equal to the Hausdorff dimension and is this Benjamini Schramm value, this value S that solves this equation star here. That's actually quite easy to prove. It doesn't really need much thought. So hunting still for the right value. Well, we tried our luck at lower bounds, and there is a general lower bound that one can come up with, which looks like this. So if you have some subset again with some box dimension value d, then it is almost surely bounded below the image of this set, or the set E in random geometry, by this value here, which is a different value, unless you have some trivial random variables. So it gives you a different lower bound. And all right, but it's a different lower bound. So maybe these bounds are not optimal. But what we'll show is that they are kind of sharp, that one can realize both of these values for constructions. And if you mess around with logs a little bit and try to get it into this KPZ-like form, you'll find that both of these bounds give you these two different values. And you see here, one of them is the log on the outside. That is what we have for the upper bound. And here the log is on the inside of the expectation. And if this random variable is not something trivial, then these two values will be different. You can always bound them one by the other, simply by Jensen's inequality. But there is some difference between these two behaviors here. And it's non-trivial behavior. All right, so what can one say? So we're interested in the box counting dimension. So we tried for a very, very long time, in fact, several years, to come up with a formula for the box counting dimension. And as it turned out, this was a hopeless endeavor. There is no formula for it for any arbitrary subset of the unit line, unless you have regularity, in which case you have the Benjamini, Schramm, Hausdorff type result. Unless you have this regularity, the box dimension is not going to be given simply just in terms of the original dimension. You have to know more about the set. So what we proved was something for a specific type of set. So for a specific, nice and simple set. That set is of the type of this 1 over n type set, this set that is accumulating at 0. So take any sequence, decreasing reals converging to 0, just to from the same framework, all of them in 0, 1. So we just have this decreasing sequence, accumulating at 0, take 0 in just to make it a compact set. Not really necessary. Makes it a nice compact set. Sure, we can throw in 0. So we now say, well, for any of these sequences, look at the set of this sequence. So that being kind of the abstract sequence, this is the set of the points in the sequence. We want them decreasing to 0, and we want them to approach 0 at the right polynomial rate, this rate p. So SP is now the set of all possible these sort of sets that we can have, where the asymptotic rate approaching 0 is p. So it's polynomially the rate p. One example is 1 over n to the p, but there are many more. It's just really just that they are geometrically similar to this 1 over n to the p. For these sets in Euclidean geometry, it's kind of a basic exercise in fractal geometry. If you pick up Kenneth's book on fractal geometry or any other kind of textbook, this will be there as an exercise or as an example. The box dimension of these sets is 1 over 1 plus p. And in fact, it's the same for any set in this class SP, not just for 1 over n to the p. It really just, dimension theoretically, they look the same. All right, so that's the dimension. And what we then proved arduously is what the dimension of that set is under this random geometry. And there it is, this ugly formula. Well, it's a formula. It tells you the value. It has a supremum and infimum, so it makes it a little bit hard to see what this actually should look like. And I will try to maybe give at least some sort of heuristic of where all of this is coming about. But maybe let's just study the statement itself. So what we're saying now is, okay, so the dimension of this set in Euclidean geometry is 1 over 1 plus p. And no matter which set you take, for all of them, kind of simultaneously, even for the same realization of W, a generic realization of W, satisfying some conditions, the dimension is given by this formula here. So it's optimizing twice here. First, you optimize in here over the infimum over t. Then this value somewhat informs the numerator, and the denominator has this log 2 in there. So if we think back a little bit to what these two bounds were, this thing here looks awfully like large deviations results that you may have seen. In fact, this is a large deviation formula that appears there. It's optimizing over large deviation exponent. So this is the top, and the bottom looks very similar to the trivial lower bound. In fact, it's just weighting between this trivial lower bound and lower bound given these P. High-level view of what this is saying. All right. How do you actually prove this? So what we first try to do is do it directly for the 1 over n to the p. Messy. There's number theory coming into this. Well, given that these are actually integers, you have to be a little bit more careful. But in the end, what's easier to prove is that it doesn't matter which set you take in this class SP. The dimension will be constant for every set in this class SP. And the same holds in Euclidean. So what we might look for is a really nice member of this class of sets SP. And this is a really good example, is the following. It is looking, as its binary expansion, just of the sets that have a certain number of zeros, followed by a 1, and then words, all the words that you could have of some length. This length is now given by this alpha. So let me maybe draw a picture. This is that. So you go down this 0 level, some k steps, and then on the right-hand side, you branch completely for some number of alpha k steps. And then you just keep one member below it. So in this case, just a zero digit. So on the left-hand side, you keep this one spine, you branch off at the kth step, and then at the kth step where you're branching off, you go down alpha k steps. And then for every one of these alpha k steps where you've branched completely, you keep just one realization, canonically the 0 in there. So this is what this looks like. And it's not too hard to show that given the way it's constructed, the number of points you have that are the same separation, which is just counting how many you have at construction level n, this also is in one of these SP, and it's in the class S1 over alpha. So waiting for alpha levels is exactly like the 1 over p exponent that we have. So all of these are also in the same class, and they are a much nicer example. Why? Well, in this example, well, what we can see is here on the left-hand side, well, we're just going down this spine up to the 0 point. And on the right, well, we're completely branching. And it turns out that this is exactly what we want on this single spine going down to 0. On this spine, we can estimate exactly what this random product, what its size is going to look like. This size here is just a simple CLT, or iterated law of the iterated logarithm. It tells us how it is growing, how the size of this leftmost interval must grow. And in fact, what it grows like is just the sum of the logs of W, like independent copies of W, take a log of them, sum them up, and exponential of that is exactly the size of this. So we can estimate this growth really well, almost surely. And then because we have a full binary tree, we can use some nice results of Ate and Barral that tells us that within those full branch trees, we also have large deviation results on the sizes at the very end. So once we've gone down to all of these, the sizes here will satisfy some nice large deviation properties, or the number of those subsets which are exceptionally large or small is well controlled. And these are the two effects that we're using here, which the latter result gives us the other condition that appeared in the theorem. Maybe let me just skip ahead briefly. Yeah, before I go there, let me give you the heuristic. So what's happening? Why do we get this weird formula? Well, we get this weird formula because on the left-hand side, we're going down this spine, and we are going to 0 quite quickly, getting quicker than we would expect because of kind of the concavity and Jensen's inequality being a strict difference between the log and the expectation on outside. It tells us that our size here is growing to 0 stronger than we would expect it to be. Whereas in these full binary trees, we're branching so much that at the end of those, we see the average behavior of the W's, where the expectation of the W's is important. The expectation of the W is here, but here it's the expectation of the log of the W. These are these two effects that are now competing. And changing this alpha allows us to vary how much these two are competing. So here's the rough argument. So we fix some value S, we fix some scale R. Bear in mind, this is a very heuristic argument. But let's look at where they split off, and let's just consider the last level at where we're at in this spine. Why this is the predominant term, I'm not telling you, but it is the dominant term in that. So the size of these leaves look like this. So we have this decay here, which is what we get down from the spine, going down n levels. And then in each of these leaves, well, we are getting a size, which is all the entire product up to alpha n, times the rescaling. So this is the density locally, and this is the size of the interval. So the size of all of these leaves is this, up to some small error. All right, so what can we do? Well, what is this size? Well, we can now estimate the number of these that are of this size by, well, how many do we have? Well, we have 2 to the alpha n. And what's the probability of this? Well, it's the probability of the size that this descendant is roughly of this scale R. All right, it looks horrendous, but, well, what is this? It's really just summing up over all of these, throw in a log, rearrange all of this here a little bit, throw in R. So the probability of this thing here being approximately this is the same as the probability of the sum of the logs of these being roughly this. Then we use large deviation results. That's the idea. Large deviation tells us, oh, it's just, well, it's given exactly by this formula, where the value of the log moment function is just what we're taking in here. We do some massaging, do some arithmetic and algebra with this, and what we end up with is this sort of expression. We do some clever substitutions. Well, this is the clever substitution. So what do we end up with? Well, we're ending up with this entire expression here as our number of sets that are of scale R, roughly, ignoring some others. Okay, it's of scale R. So let's rearrange everything. So log n over log R, plug everything in, massage a little bit more, resubstitute, and voila, we're getting the formula that we had at the end. And this is also why we get this infimum in here. This is the large deviation that you get in this full tree on the right everywhere. And it is offset by how fast we are shrinking along this common spine. That's where this problem is. We have this common spine where everything goes to zero a bit quicker than one would expect. Whereas on these full binary trees on the right, you get this averaging out behavior. Okay, so that's enough with all of this, but let me maybe just kind of highlight what are the important things, the important takeaways here. Well, firstly, the upper lower box counting dimension, they must exist. There are some numbers. It's a tail event, so there must be something. But the box counting dimension no longer depends on just this random variable. So if you think back the KPZ type equation, it was just in terms of the Hausdorff dimension of the original set. But now we also need the structure. But because we need the structure, we can have two different sets with the same Hausdorff or the same box dimension, but with different dimensions under random geometry. That means there cannot be such a KPZ equation. You can create all sorts of sets that have different dimensions, that have the same dimension in Euclidean, but not the same in the random geometry. So any sort of result must take into account more structure information. So I'll leave with kind of the question of, well, what is this structured information? How can one capture the structured information? We don't quite know. We've tried several things, but more is needed to capture something about the set to know what it looks like in the random geometry. And maybe there are dimension profiles involved, so I didn't really talk about them. I'll ignore them. Just say thank you very much for listening.
Thank you for your nice presentation. Let me stop the recording.